Hello everyone, my name is Maجد البراشي and I'm from Southwest Jiaotong University, China. Welcome to our paper presentation. This is our paper ID. Our paper title is Fully Integrated TLCL Filter for Grid Connected Converters to Reduce Current Harmonics. These are all the authors from Southwest Jiaotong University, China. Outline, introduction, background, methodology, novelty of proposed solution, results, and conclusions. Introduction. This paper proposes a trapped LCL filter which has an LCL trap at the inverter side. The filter utilizes only one magnetic core for the three windings, trap, grid side, and converter side windings. The mutual inductances between these coils are utilized to improve the output current quality. The network is supposed to be weak and modeled as a series connection of ideal voltage source and a network inductor. Background. In literature, various modified configurations of LCL filters has been presented, which has LC traps resonated at the switching frequency and its multiples. The LCL filter capacitor was substituted with an LC trap connected in series, which is known as an LLCL filter. The grid side inductor of the LCL filter is substituted by a parallel LC trap, which is referred to as LCCL filters. The trap filters harmonics elimination could be increased in case of using more than one trap, like the LTCL and SPR-LCL filters. A general drawback of the trap filter is the extra filter elements. Adopting the magnetic integration method is one approach for overcoming this drawback. The LCL filters inductances were wound on one magnetic core, but the mutual inductances were not used entirely. This paper presents a fully integrated trap LCL filter, which called the fully integrated TLCL filter. This is the three windings of the trap. As we see, this is the grid side and this is the inverter side. This is the LCL filter and this is the trap. All the three windings of the trap and the filter are wound on one magnetic core, as we see here. This is the central lamp and these are the two side lamps. All the three windings are negatively coupled based on the flux direction in each lamp. The LC trap is built by connecting a capacitor CT in parallel with LT. The proposed filter adopts one magnetic core in which the cross-section of central lamp is double that of the side lamps. This type of integrated filter inductor could accomplish the minimum size in comparison to the discrete inductors and integrated LTCL ones. Methodology. The fluxes produced by these windings, as in these equations, phi t is the flux produced by LT windings, phi ti is the flux produced by LT windings flows through Li windings. The same way is for the flux produced by phi t by LT and flow through Lg. By the same way, we can get the flux produced by Li and the flux produced by Li and flows through the two other windings. Also, we can get the fluxes produced by Lg, the grid side inductor. The self-inductances Li, Lt, Lg could be defined as follow, with the constant μ0 represent the air permeability. This is Lt, Li, and Lg. By the same way, the mutual inductances Mti, Mtg, and Mig could be described as follows. This is Mti, Mtg, and Mig. The inductor voltage Vt, Vi, Vg could be then defined by this way. From this equation, we can notice that the three wind inductors are coupled with each other. The magnetic resistors Rt, Ri, and Rg determine the self and mutual inductances, which can be obtained in the following equations, where the length of the ear gaps of the central and side limbs are indicated by LGC and LGS respectively. Here are the RT and RG, and this is the RI. The ratio between the mutual inductance and the square root of the product of mutually coupled self-inductances is known as the coefficient of coupling as follows. This is the coupling coefficient between Ti and Ig. They are the same one. And this is the coupling coefficient between Lt and Lg. Novelty of proposed solution. The harmonics in the EC voltage source are mitigated by a passive filter. The LTCL filters include an additional LC trap compared to the LCL filter. The LC trap are resonated around the switching frequency, Fs. All the switching harmonics are introduced around the doubles of switching frequencies because of the unipolar sinusoidal pulse width modulation. One LC trap is desired and is therefore discussed in this research. The planned model of the inverter filtered by the fully integrated TLCL filter can be expressed as the following. From this transfer function, we can see that this transfer function has two magnitude traps at the frequency omega t. The switching harmonics can be mitigated if this frequency is adjusted to double switching frequency. Both diagrams indicate that there are no resonant peaks. Here are the both diagrams of the fully integrated TLCL filter. As we see, there is no resonant peaks, and also we have two trap resonant at the same point at the double switching frequency. Results. Simulation and HIL hard-in-the-loop models were developed. The coupling coefficients are optimized for adjusting the two resonant frequencies, as we see, at the double switching frequency. The two-level sine triangle symmetrical regular sample pulse width modulation is used in this paper. Here are the values of the system parameters. All the system parameters are described here. Here are the simulated waveforms with network, with weak network. This is the grid side current, inductor side current, grid voltage, and DC link voltage. As we see, the grid side current Ig waveform remains sinusoidal. This is implying that the low order harmonic mitigation works well. The grid current is not distorted by the low order harmonics. This is in conjunction with the theoretical analysis. Here are the spectra of the grid side current. here, and the inverter side current. As we see, the Harmonics diminution at the switching and multiple switching frequencies is strong. There is also significant harmonic absorption at the low frequencies. The harmonics of the double switching frequency were decreased from 9% to 0.1% in the grid side current. The harmonics of the fourth and sixth harmonic switching are reduced from 1.9 and 0.5% to 0.29 and 0.1% in the grid side current, which they are lower than the limit. The proposed filter can meet the IEEE standards with a total harmonic distortion value of 1.27% in the grid side current. Here are the transient simulation results of the fully integrated TLCL. This is the grid side current, inverter side current, grid voltage, and DC link voltage. To analyze the reliability of the proposed filter, it was tested under variable loads with 25 ohm step-up transition in the DC load at the time of 0.5 seconds. As shown, although the load was changed more than 33%, but during the transient time, the proposed filter also shows good switching harmonics absorption capability. Here are the experimental results. As we see, this is the grid side current, inverter side current, grid voltage, DC link voltage. The hardened loop experimental results verify the simulation results in that the proposed filter has removed most of the harmonic components. It's clear that the current waveform is significantly improved by adding this proposed filter. The total harmonic distortion is reduced from 15.2% to 3.9% in the grid side current, which satisfy the criteria of grid codes. Conclusions. This paper explored the benefits of the fully integrated TLCL filter as following: decreasing the number of discrete passive elements, realizing the filter design flexibility by the magnetic integration strategies, high switching frequency absorption capability, thus reducing the total harmonic distortion, deleting the resonant peaks without any RC damper, high reliability against the load variations and the impedance of the source. Thank you. Our presentation is finished, and I hope we see you next time. Goodbye.